אנחנו מארחים היום את בוריס שוסטין מאוניברסיטת תל אביב. כמו שאתם אולי יכולים לנחש מהכותרת, הוא ב-Applied Mathematics, לא במדעי המחשב. והוא ילמד אותנו קצת על המשינרים מאחורי האופטימיזציות שאנחנו עושים בהרבה הקשרים.
אוקיי, תודה. אז בסדר אם זה יהיה באנגלית. Okay, so thank you for having me here, and thank you for the introduction and the intro lecture that was before. The work I will be presenting here is some of the work that I did during my PhD, and this is a joint work with Jaime Von, who is my supervisor, William Moore, who is a lab mate, and Barak Sover, who is a faculty here, but in another department. So first, I would like to describe the problem setting that I'm interested in, and it will be related to the introduction that you previously saw. So I'm interested in solving optimization problems such that the search space is a smooth manifold. Now I'll show some examples of where these problems occur, but indeed, as in the introductory lecture, we can encounter such problems in many areas of even machine learning, in PCA, matrix completion, and many others. And in this lecture, what I will show is how can we deal with two challenges that arise when we have such problems. So once we have a manifold, it means we have some underlying geometrical structure that we need to work with, a constraint that we need to satisfy. And so we need to form its geometry. And in many cases, its geometry might be either too hard to construct due to intractability or maybe lack of information. And since we're dealing with optimization, we want to somehow control the number of iterations. So we will see two approaches. One approach is Riemannian preconditioning combined with randomized numerical linear algebra with matrix sketching. This approach is aimed at dealing with high computational costs. And if time permits, we will also talk a little about how can we deal with lack of information, where we will use manifold learning. Okay, so let us begin with some introduction. So first of all, what is Riemannian optimization? And before I dive into that, where can we encounter problems of optimization problems with a manifold constraint? So again, thanks for the previous introductory lecture. We saw that these problems arise in computational science, physics, even in deep learning. I'll say a word about that a little later. And more specifically, I'll show three specific problems that can be formulated as optimization and manifolds. The first problem is finding eigenvalues of a symmetric matrix. Now, if we have a symmetric matrix and we want to find its maximal or minimal eigenvalue, we can actually find them by solving these optimization problems of this quadratic function, where our variable is constrained to lie on the sphere. Now, the sphere is a n-1 dimensional manifold in Rn. Another problem that, again, was previously mentioned was the PCA problem. There are many formulations for the PCA problem, but we can also formulate it in the following way as an optimization on manifold. In what sense? We have a set of data points, and what we're trying to find is a linear subspace of a dimension of our choice, for example, P, such that it is the closest subspace with respect to some distance to these data points. Now, this manifold is a bit more abstract. It's the set of all linear subspaces of dimension P in Rn, and it's called the Grossmanian. And again, another example from machine learning is indeed the Netflix problem, the matrix completion problem, we have a matrix that only parts of its entries are observed, and we assume that this matrix has some underlying low-rank structure. Right? We can think of it as similar users, or similar features, and so on. And what we are trying to find is a matrix that would be as close as possible with respect to some metric to our given matrix, such that this matrix is a fixed rank matrix, a low rank matrix, and this object is also a manifold. So this is just to convince you that we can encounter these kinds of problems in various places. There are many other examples. And the next question I want to answer is, how can we solve these kinds of problems? Now, I guess some of you are familiar with optimization problems such as optimization methods, such as gradient descent, the Newton method. You might have heard of them. We'll see specific formulas soon. But what can we do when we have constraints? So there are quite a few methods to address these kinds of problems, such as the projected gradient descent that I'll describe in a few moments. But there are many other methods. For example, we can add a penalty function to our cost function that will penalize us for each violation of our constraint. Now here, the framework that I'll be working with is Riemannian optimization. And I want to convince you that when we have constraints of the form of a manifold, that would be a natural choice. I'm not saying it's the best one, but it's, in a sense, a very natural one. How come? So, first of all, probably the closest in spirit to Riemannian optimization, at least for Riemannian gradient descent, is the projected gradient descent. What is the projected gradient descent? Suppose we want to solve an optimization problem with some constraint. For example, as we saw, we would like to rely on the sphere, for example, when we find extreme eigenvalues of a matrix. So what we do in projected gradient descent? First of all, we completely ignore our constraint. We perform a gradient step. And then we suddenly recall that we need to satisfy somehow this constraint, and then we project back orthogonally our step back to the constraint set. Now, what kind of problems can arise here? Suppose that our constraint set is this table, right? So, and let's say that our gradient points almost perpendicularly to this table. So we perform a step, and then we project back to the table. If we look at the step that we performed on this table, it's very small. We wasted a lot of energy of going out of our constraint and coming back. So first of all, it's inefficient. And, well, a second problem is that who said that projecting is an easy task? It's an optimization problem of its own. And it might be as hard as solving the original problem. So the idea or the philosophy behind Riemannian optimization is somehow solve our optimization problem in an intrinsic way. What do I mean by that? We want to use the geometry of our constraint such that we will take unconstrained optimization methods and generalize them to the manifold setting. So let's take a look, for example, on the gradient descent, on a standard gradient descent iteration. What do we actually do here? We have some object that is called the gradient. We need to define what it is. And we also walk along the domain in the sense that we have here vector addition. Now, if we are on a manifold, which is not necessarily a linear manifold, once we perform vector addition, we might leave our constraint. And the idea would be to somehow walk along this manifold. So, indeed, the idea is to somehow form a set of geometric components. We don't actually need a full description of the manifold. We just need a set of components And once we have them, we can generalize optimization methods that we use and use in the unconstrained setting to the manifold setting. Now, for those of you who want to read a bit more about this topic, these are two great references, really recommended. And now let's dive a bit more into the details and talk about what is the geometry that we need to form. And
so maybe you're going to say this, but if you do projected gradient descent and the step size is infinitesimal, then it's the same, right? You're not. The direction after you project it is the same. Is that true?
Almost. They are close in spirit, but I'll mention two differences. They are almost the same, but okay. So I'll
wait for this.
It's partially answered here and partially in the next slide. So, okay. So the idea is as follows: we need a set of geometric components that once we have them, we can do this generalization. And the way it's written here is the same way that you can code your optimization method. It's a class with these methods. You need to realize these components. Once you have them, you just plug in to your optimization, to your favorite optimizer, and you just plug and play. So here I'll show how can we generalize gradient descent to be Riemannian gradient descent. So what we need is, first of all, tangent spaces, which are local first-order approximations of our manifold. Right, we are on planet Earth, but locally it all seems flat. And the nice thing about tangent spaces is that these are linear spaces, so we can perform all the operations that we know and love from linear spaces on this tangent space. But once we do these operations, we need to somehow return to a manifold. And the object that does it is a retraction map. It's a mapping between the tangent space back to the manifold. It could be a projection, but we can generalize it to things that are easier to compute. There are two examples here. If we are in Rn unconstrained, so a retraction map would be just the identity. Everything is the tangent space. If we are on the sphere and we want to stay on it, so what we do, we just normalize our vectors. Now, to be a bit more abstract, the idea is to locally follow geodesics, but I don't want to go into these details. So projections would work, and also some generalizations of them.
Okay,
Yes.
So both examples that you gave are actually projections.
Yes. But you can use simpler ones. Actually, so the simplest thing you can do is actually a first-order approximation of a projection, or in other words, if you can follow the geodesics. Okay, it's going. Okay, so following a geodesic is the exponential mapping, and you need to solve a second-order differential equation to know exactly what is the geodesic. So actually, it is enough to have a first-order Taylor approximation of this mapping, and it would be a perfectly fine retraction. So, for example, projections satisfy this, but it doesn't have to be. Okay, so this is these are the first two components, and there is another set of components which is important for our definitions of the gradient and the Hessian. In what sense? So once we have these tangent spaces, linear subspaces, we want to say how we measure distances on them. So we want to define an inner product on them. this inner product, if it will rise smoothly between those tangent spaces, is called the Riemannian matrix. Once we have a Riemannian matrix, we can define the Riemannian gradient, which is a vector on the tangent space, and the Hessian, which is a self-adjoint linear transformation between the tangent space to itself. So these are generalizations of the gradient and the Hessian that you know from the Euclidean setting. And a simple example would be for a submanifold. What is a submanifold? A submanifold is a manifold that lies in a larger space. For example, the sphere. In R3, we have the sphere on R2, and the Riemannian gradient would be an orthogonal projection of our standard Euclidean gradient to the tangent space. So this object tries to solve the second problem that we have with projected gradient descent. In projected gradient descent, we waste a lot of energy on leaving our constraint. Now, the best, in a sense, thing that we could do is be as close as possible to the constraint. So in this example, the tangent space is the table itself. So we just walk along it. And in more complicated examples, at least locally, it's a good approximation of the manifold. So we kind of stay close. Okay, so there are, of course, many other components, but the list of components that I gave here is enough for the Newton method, the gradient method, conjugate gradients, and many other methods that you love and use. Are there any questions so far?
I always say this thing about wasting energy. You're not really moving. But mathematically, if you for a linear subspace, certainly, if you calculate this gradient, then you project it down, that will give you the same solution as calculating this gradient, right?
Right, yes, because that's a projection, right.
So there's no, so I'm not, I still don't understand the difference between projected gradient descent and what you're suggesting for small step sizes. I understand for large step sizes, all the approximations no longer hold.
Yeah, so the two main differences is that you don't have to project. You can use easy operations to return to your manifold. And the other thing is that in projected...
And again, for small step sizes, projecting is easy because everything is, right?
Well,
if the manifold is locally linear, then projection operator is easy.
It depends. It's an optimization problem on its own. It might be quite hard to solve it. But yeah, again, the thing is that, okay, the intuition that I give here is for submanifolds, but you have abstract manifolds that do not necessarily lie in a larger space, and the notion of projection is not exactly clear there. But that just for this is just for intuition.
Maybe it would be helpful if you can give one example in which the operation that retracts you back to the manifold is not a projection.
Yeah, so, okay, so I don't have the explicit formula here, but I mean, for the sphere, the geodesics are large circles. So a retraction would be to move along a large circle up to a certain point. This is what is...
The retraction that you wrote here is exactly projection.
Yeah, that is a projection, right. The explicit formula for large circles would be... great circle would be with cosine and sine. Don't have it here, but just move along the... this illustration tries to kind of show you how do you call
a great circle.
A great circle, yeah. It tries to illustrate it, yeah. So that's one example. There are many others, and
Shai is asking, and in this case, will the optimization step will be different than had you performed?
Yes. So okay. So the projection here is only a second-order Taylor approximation of walking along these circles. If you can walk exactly along these geodesics, then your optimization method would be more exact, and you can also advance with larger step sizes. These are the two things.
Again,
yeah.
For the simpletons here, like me, is it simply using a different parameterization of the optimization problem? For example, if you want a sphere, then instead of representing it as two-dimensional, so if it's two-dimensional, for example, two-dimensional, instead of two-dimensional, you get just one angle. And then you reparameterize the problem using the angles instead of the Euclidean representation.
You can do this as well, but that's what I show here is, well, again, in many examples, the optimization problems that we're given are they have a cost function which might be defined in a larger space, but we have this constraint that tells us that we have to find a solution just on our constraint set, and the idea here is to use this intrinsic geometric representation in a sort of philosophy that tries to mimic the unconstrained setting to the constrained optimization setting. Again, we can solve this problem with Lagrangians and many other methods that just ignore the fact that we have here a specific geometric object, which is a manifold. So here we take advantage of the fact that this is a manifold, and we can use this set of components to still work with the extrinsic coordinates, but with these operations we can satisfy the constraint at each iteration. So
what property of sorry, I'm still not answering. What property of the manifold are you using?
In what sense property? Different than these components?
This is not a definition. I mean, you're saying that if you go back to so there is a retraction map.
Yeah.
Okay.
Yes.
This is a property that you're using. You have a retraction map.
Yes. For okay. So I need okay. Maybe we'll.
Projection is something that is well defined. You have a point of start of the manifold, and you want
not
to
necessarily.
find the closest point on the manifold.
Right, and you don't necessarily have a unique solution, right? It's not necessarily well defined. It's if your manifold is something.
Yeah, it's not unique, but it is well defined.
I think you can find problems when solving it would be as hard as solving the optimization problem, but again.
Just I understand what it means.
Okay.
It means find a point on the manifold which is which has minimum distance to the point that you are starting with.
Yes.
What is a property that you are requiring from a retraction map?
Yeah. Okay. So it has to be a first-order approximation of the exponential map, which is a map which walks along geodesics. But again, maybe we'll take it offline because I don't want to get too much into the mathematical details. Okay. We can take it offline.
Maybe if you want, just to answer Shai's question, an intuitive example is if you want to take the shortest path from here to San Francisco, if you were to do it with projected gradient descent, you would go directly west from here, which is wrong. You have to go north to go north. So projected gradient descent will give you a suboptimal path for this particular problem, whereas if you walk along the geodesic, you would figure out that you have to go north.
Well, okay, again, if you want the specific mathematical properties of the retraction, you need a map that satisfies both of these things, and then, okay, again, okay. This retraction map, what it does, it connects a point on the tangent space to the manifold. So if we have a function which is defined in a larger space, then what we can look on is this new function, right, this composition, and that would be a function that receives a point in this linear space and returns a point on a scale, right? So this is a standard scalar, a standard function in R, whatever the dimension of the manifold is. Then we can take, for example, a Taylor expansion of this object, and then we can reason about what is the gradient and Hessian and so on. So that is the underlying object that hides in this description of Riemannian optimization. So that object is already something that we can work with, like in unconstrained optimization. So I hope it gives some intuition, but the object that I described here, without going too much into the details, are actually Taylor expansion of this object, and that is why we need both of these properties. But let's keep it there. So okay, so one important thing that I want you to take from this slide is note that the choice of inner product, the choice of metric, is very important, and in the sense that both the gradient and the Hessian depend on it. So in what sense? Actually, the choice of metric is very important to the at least asymptotic convergence of various optimization methods. It is true for unconstrained optimization and for constrained optimization as well. For example, once we choose the Riemannian metric, then we also get the Riemannian Hessian, and if we look at its condition number at the optimum, which is defined here by this kappa, the ratio between the maximal and minimal eigenvalues, then this constant affects the asymptotic convergence of our iterative method. Now, generally speaking, this is actually the choice of Riemannian metric is a form of preconditioning, and I want to give you an intuition to that. So in RD, if we try to understand what are the components that I described previously, so the retraction would be just the identity. And if we use the standard dot product as the Riemannian metric, then our gradient is the standard gradient, and as a result, the gradient descent is the gradient descent that we are all familiar with. Now, if we change the inner product, for example, we have here a weight matrix M, which is a symmetric positive definite matrix. Then our gradient changes. We have this matrix inverse that pops out. And our Riemannian gradient method, as a result, becomes almost the same iteration, but with this inverse. Now, if you take this matrix to be the Hessian with the hopes that the Hessian of the cost function is symmetric positive definite, then you retrieve the Newton method. This is one example. Another example is with linear systems. In linear systems, when we try to solve Ax equals b, we can formulate this problem for positive definite A as an optimization problem of this quadratic function. Now, we can solve numerically this linear system, for example, with the Richardson iterations. And they're actually equivalent to using gradient descent to solve this problem. Now, the convergence of the Richardson iterations depend on the condition number of the matrix A. So the classical idea of preconditioning is let's somehow manipulate our problem such that this condition number is improved. That is preconditioning. Now what we can do is we can take the system Ax equals B and multiply by some matrix this system, and now solve this thing. Now the hope is that by multiplying by a matrix that reduces this condition number, we will have lower condition number and as a result faster convergence. So in this example, choosing a different inner product is actually equivalent to this classical preconditioning that I showed here. Now, what is the best matrix that we can choose? What would make this condition number, which is the ratio between the eigenvalues, the extreme eigenvalues, to be the best? Now, right? But what is the problem? If we had A and we could invert it, then we don't need an iterative method. We already have the solution. So that is exactly the phenomena that we also encounter in many other problems. And the question is, what should we precondition and how? So this is what I will try to answer here. So specifically, in this talk, I will focus on optimization problems with orthogonality constraints. It means that our variables are constrained such that they need to be orthogonal with respect to some weight matrix, Bi. If it's the identity matrix, then these are just standard orthogonal matrices. And for dimension 1, this is exactly the sphere or an ellipsoid. The formal name of this constraint or of this manifold is the Stiefel manifold or generalized Stiefel manifold. And the standard inner product that is typically used for these manifolds is this trace inner product with the weight matrix B. What's the idea behind that? If we make a change of variables such that y equals the square root of b times x, then we return back to the standard orthogonal matrices or the sphere instead of an ellipsoid. So that's the motivation behind choosing this inner product. And
B required to be positive semi-definite or something like that?
Yeah, B has to be positive definite. Yeah. And I want to present here a specific problem, a specific optimization problem that motivated our work. So the problem that I'll describe here is canonical correlation analysis. What is canonical correlation analysis? So we have two random vectors, and we want to find a linear transformation that maximizes the correlations between these random vectors. This is used for feature extraction, dimensionality reduction, and many other applications. But typically, we don't have an analytic form of this x and y. What we actually have is samples. We have data matrices where the rows are the samples of these random variables and the columns are the features. So we have x and y here. And in the language of linear algebra, what we try to do is we maximize this trace with respect to u and v such that u is an orthogonal matrix with respect to this sigma xx, and V is also orthogonal with respect to sigma yy. Now, sigma xx and sigma yy are both covariance matrices of our data, and this is, in many cases, we have a lot of samples, and we have tall and thin matrices, and actually forming these matrices is a bottleneck in many computations. So we can either focus on finding only the top correlation, then our problem is reduced to a quadratic problem subject to two ellipsoids, or find multiple correlations all at once. How do we solve it? What's the baseline? What am I competing with? There is a classical algorithm, the Bjork-Golomb algorithm, which uses the QR decomposition and an SVD decomposition. And the bottleneck lies in this QR factorization. This QR factorization takes O and D square operations. So this is what I'm trying to beat here. And okay, so this is a direct method of solving. So once we're not satisfied with a direct method, we try and use an iterative method with the hopes that only vector products, only matrix vector products would be faster, and we hope that there will be no too many iterations. So, okay, there exists actually an algorithm. There are many algorithms, but there exists a classical algorithm of solving canonical correlation analysis. This is the alternating least squares algorithm, where in each iteration we freeze one of the variables and solve the least squares problems for the other. The problem is that we need to invert here the covariance matrices of the data. This is very costly, and specifically speaking, it costs, again, ND square operations. For very large data matrices, this is bad, since this is as expensive as a direct method. And what I want to show is that by using Riemannian optimization and Riemannian preconditioning, we can actually beat it. So a nice observation that we have is that actually the canonical correlation analysis problem is an optimization problem which is constrained on two Stiefel manifolds. And the alternating least squares algorithm is actually a Riemannian gradient descent with the standard matrix. Now, I can list all the components that I showed you before for this specific manifold.
There's no step size. Is there a step size on that?
So you can choose the step size in many different ways. You can use the standard methods of fixed step or backtracking.
No, but the way you formulate the alternating minimization.
Oh, right. So
it's size.
Yeah, it is with a specific step size. Right. I just ignored it, but yeah, it's with a specific choice of step size. You are correct. That it means that someone is listening. Thank you. And okay, so this is the standard Riemannian gradient descent with the standard matrix. So this is the list of components, and the question is where the bottleneck lies. Where is the problem? So if we use the standard matrix for this manifold, then we have these covariance matrices here. And the problem is that for the gradient computation, their inverses pop. So what can we do? Let's just change the inner product or the Riemannian matrix. Okay, so we can do that. We can replace those matrices sigma xx and sigma yy with two symmetric positive definite matrices. I'm not explicitly saying what they are, but once we have them, we can define again all the long list of components that we have, the gradient, the Hessian, and so on. And even though the formula looks a bit more scary, in terms of computations, it's the same.
You replace the matrix, so the inner product is different. So
right.
I assume
so
the cascade everything later is different. So
right.
Why do you assume the optimization will lead you to the same place?
Oh, okay. Okay, great. So great question. So okay. So I'll partially answer this question here, and then okay. So I'll start with this explanation. So a great question. What is the effect of actually changing this inner product, right? So what I'm interested in is, before asking to which point will I converge, I'm asking what would be the effect on the number of iterations. So I'm looking at the condition number of the Riemannian Hessian at the optimum. As I previously mentioned, at least for the asymptotic convergence rate, it governs the number of iterations. And so the theorem that we have here is that for taking these, replacing the sigma xx and sigma yy in the inner product with some general matrices, m xx and m yy, we can have this bound on the condition number. We have here two terms. The first term, kappa CCA, is a term that only depends on our given problem. Those sigmas here and mu here are the canonical correlations that we're trying to find. And this kappa here, this is the generalized condition number of the matrices sigma and m. Now, the generalized condition number of these two matrices is the condition number of the following matrix. Sorry. Minus sigma. So that's a more friendly equation for this generalized condition number. And again, what we can see here, what is the best bound that we can achieve? By choosing m to be sigma, then as in the example of linear equations, we get the best bound for the number of iterations, for the condition number, and as a result for the number of iterations. But how can we use it? And how can we explicitly choose m such that the computational cost is better while this bound is not worse? So we're trying to balance the computational costs and the condition number. Okay, so how can we do it? So the idea is to use a tool from numerical linear algebra called matrix sketching. So I'll say a few words about matrix sketching, and then I'll return to this problem. What is matrix sketching? So matrix sketching is a tool of randomized numerical linear algebra. It's a collection of randomized dimensionality reduction techniques, where the idea is to take large input data matrices and somehow make them smaller, so that the problem that we solve would be easier. And hopefully, by preserving some properties, our solution would be not very far from the original problem. So one example for this kind of matrix sketching is the count sketch matrix. In count sketch matrix, we have the following. We have a random diagonal matrix with different signs on the diagonal. And we have a matrix H, where in each column of this matrix, we have only one non-zero element. So what this transform does is mix the rows of our original matrix with different signs. And the idea is to take these kinds of matrices such that the number of rows S is much smaller than the original number of rows N. So what is nice about matrix sketching? That first of all, it's fast to compute. For example, if we want to apply S on our data matrix, it only requires the number of operations that is required is the number of non-zeros in our data matrix. And as a result, it is also easy to find the inverse of the sketched data matrix, which is exactly the bottleneck in our computations. And on the other hand, it helps us with preserving some properties such as matrix multiplication. So I'll skip the following few slides just to show what we can do with both of these properties. So the idea is that, for example, in the canonical correlation analysis problem, we have a constraint of the form of a covariance matrix with some regularization here. So what we're going to do is we're going to replace this constraint with a sketched version of the data matrices. After we apply this sketch, which is fast to compute, we can actually prove that the condition number with high probability of the original matrix and the sketched matrix is bounded by a constant. So that is exactly the key for the preconditioning strategy that I use here. So for the canonical correlation analysis, what we can do is replace the data matrices X and Y with their sketch versions. And then the condition number of the Riemannian Hessian is bounded after choosing these matrices M by a constant. And it doesn't matter what was the original condition number of sigma XX and sigma YY. So on the one hand, the number of iterations is somehow controlled, and on the other hand, the number of operations due to this sketching is much smaller in the sense that we don't need to perform ND square operations anymore. The bottleneck was in finding the inverse of the covariance matrices, and this is what we avoid here. So I have a few numerical examples. One example is with the MNIST dataset. I know it's a simple one, but it's not a supervised learning problem. All I care about is that I have this large data matrix. I don't care about the labels. And what we did is we split the data into two halves. And what we try to recover is the top three correlations of these two halves of data sets.
Two halves meaning not each sample is in one data set, but each image was split half and half somehow?
Yeah. Exactly. So the images in the MNIST data set they have 784 pixels.
So, and was there a specific way you split it, or you didn't care?
No, just in two halves. I just wanted to there is a correlation between.
From a mathematical perspective, you can split it to the even and odd pixels, and you can split it to I split the matrix into two halves. I mean, we could choose other things. It's just what I try to demonstrate here is that indeed I can recover the correlations between the two halves of this data set. So what you can see in this graph is the number of iterations with respect to our error, the suboptimality. And the number S here is the number of rows that we used in our sketching. So we began with two large matrices with 60,000 rows. And what you can see here is that even with around 2,000 rows, the number of iterations that is required to reach to a nice arrow would be quite close to using the original data matrices as matrix. But what we earn here is that instead of using matrix operations with 60,000 row matrix, we are reduced to 2,000 rows. That's one example. We have another example here with a second order method. It also works there. And we also applied, the canonical correlation analysis problem is just an example. In many other problems, when we encounter this covariance matrix structure or Graham matrix structure, then we can try and apply our method. So another example that I want to show is the Fisher discriminant analysis, where in Fisher discriminant analysis we have a data matrix where the rows are samples and each row has a label and the columns are the features. So linear discriminant analysis is a method for example for dimensionality reduction. And the idea in this dimensionality reduction is to help us in classifying each of the classes. So what we do is the following. We try to maximize the distances between the means of each class and minimize the variance of each of the classes at the same time. We search for these kinds of projections, and they will be helpful in later on. That's a pre-processing step for classification or other tasks. So in the language of numerical linear of linear algebra, we can formalize this problem as an optimization problem subject again to this orthogonality constraint or to this ellipsoid. And similarly to the canonical correlation analysis problem, a direct method would take O and D square operations, and without going too much into the details, we can similarly find a bound on the condition number of the Riemannian Hessian. This bound tells us how or what should we precondition, and by using matrix sketching, for example, we can achieve a good bound while preserving nice computational costs. Okay. So, I have another example, but I'll skip it. I want to say a few words about a different problem that I was working with Barak Sover here. So these are the references for those who are interested, and the other question I'll take offline. And I want to use the last couple of minutes to present a different problem, a similar but different problem setting. So far, we use numerical linear algebra to accelerate costly operations in optimizations on manifold. Now here, I'm in a different problem setting. Again, I want to solve optimization problem on manifolds, but due to lack of information, I cannot form the geometric components that I need in order to perform optimization. So the motivation comes from the works of Barak Sover. He was working, for example, on manifold learning in the setting of archaeology, for example. He had data sets of ancient handwritings, and the underlying assumption was that handwriting of the same person would belong to the same manifold. So Barak developed a manifold learning technique, which I use here in order to perform optimization on manifolds for such cases, for cases where manifold is abstract, for images of a certain class and so on, and we cannot form the components that we need. So in Barak Sover's work, manifold moving least squares, it's a manifold learning techniques that does the following. We have only samples of some manifold, and in order to approximate this manifold, we perform two steps. First, we find a plane which would be as close as possible to these data points. This would be a reference plane. And then we're performing polynomial regression to actually approximate the green line here, which is the manifold, as a graph of a function from this plane to the manifold. Now, if we take this method, we can actually form almost all the components that we need in order to perform, at least approximately, optimization on this unknown manifold. For example, we can approximate the tangent spaces, the retractions, the gradients, and we can even approximate gradients of functions that are only given through samples. This is zero-order optimization. We can prove that all these components converge to the original components, and they converge with their convergence depend on age, which is a sort of distance between our samples. We can actually prove that using our approximate components, we can at least achieve a first order optimality condition after a specific number of iterations. And what I want to present is two examples of our algorithm. The first one is we have this weird manifold in R100. We have here x1, x2, a sine function, and ones from there on. And we have this simple function. It's just a toy example. But what I want to emphasize here is that our algorithm only receives samples of this cost function. It does not have access to the analytic form of this function, and also not to the manifold itself. And by using our approximate components, you can see here on the graph, in red, these are the steps. Dark blue is lower values of the function, and you can see both in the ambient space, well, at least in R3, I cannot paint in R100, and also in the parametric space that indeed our algorithm, at least locally, achieves the minimum. And one final example is, again, with PCA. We saw previously that PCA can be formulated as an optimization problem on manifolds. And we can formulate it again with we show here that we can use only samples of the manifold and the cost function. And what you see here in the graph in red is a method that has all the analytic expressions for the manifold. And in blue and green, you can see our method with noise and without noise that only approximates the manifold and the cost function. It's the error against the number of versus the number of iterations. Yes. Okay, so this is it for this presentation. So the next step with this would be to somehow apply our method to real-world applications, because in many real-world scenarios, as in archaeological mathematics or evolutionary mathematics, we don't actually have an explicit form of the manifolds, but we do want to minimize some cost functions, so that would be our next goal. And this is the reference for this work. Thank you. Yes. Any other questions I can take offline, or maybe to everyone?
Maybe time for one question.
So can you use the sketching idea for projected gradient descent as well?
Yes, I mean, also, again, in the projected gradient descent, I can also play with the inner product. Once I change the inner product, my projection changes. And so if I change the inner product and use a sketch version of this inner product, then I'll achieve faster convergence. So yeah, it will also work there. I mean, you can apply this sketching method on an unconstrained problem as well. So that's definitely. Any other questions? Thank you.